For this video on integration by parts, we will be covering two indefinite integrals, two definite integrals, as well as a tabular equation example and its use case as well. So when do we use integration by parts? Well, we use it to find the integral of a product of two functions, for example, sine of x times the square root of x. And you might be wondering, well, couldn't we use u substitution? If we chose any of these for our u, it would not cancel anything out. So you have to use integration by parts. To think of it, it's also the reverse of product rule for differentiation or finding derivatives. Now the formula for integration by parts is the integral of u dv equals uv minus the integral of v du. And you will have to memorize this equation, and it's not too hard. I just like to think of it as the university of very dope undergrads, which is uv for university and uv, and then very dope undergrads for v du. Now you will have to memorize the minus as well as the integral, but I feel like that's fairly easy. Now to explain why the formula has these variables, we just want to know that our u is something we will differentiate and our dv will be something that we want to integrate. Now you might be wondering, how do we figure out these variables? And that is going to be through ILATE. Now ILATE will help us choose our u, and it stands for inverse, trig, logarithmic, algebraic, trigonometric, and exponential. And again, these are all to help find our u. And think of it like a priority list. And don't worry, it may seem confusing, but I will give an example. Now our first problem won't be too hard. We'll just do an integral of x times e to the x dx. And a good habit to form is to always write down the formula you are about to use, which in this case is the integral of u dv equals uv minus the integral of v du. Now our initial step should be to find our u first, and in this case we will use our ILATE method. Now are any of these inverse trig? No. Are they logarithmic? No. Are any of them algebraic? Yes. That's our x. Are any of them trigonometric? No. Are any of them exponential? Yes. Our e to the x. Now again, I said to treat this like a priority list from top to bottom, so x will be our u. Now we'll just find the du of that, which is the same as dx. Our next step is to find our dv, which in this case is e to the x, because that's what's left in this. We already used up the x. Maybe I shouldn't use white. We already used up the x, so the rest of the problem is e to the x dx. And our v is going to be the integral of our dv. So we know the integral of e to the x is just e to the x. And how this relates to what I explained earlier is that, remember, our u is going to be what we want to differentiate or take the derivative of, and our dv will be something that we want to integrate. So solving this will be fairly simple now. All we do is just plug in to this formula. So we know our u is x, our dv is e to the x dx, and that will set equal to x times e to the x minus the integral of e to the x dx. We then find the integral, which turns out to be e to the x, and then don't forget to add our constant. And there we go. We solved our very first integration by parts. Now for this next problem, I want you to try to solve it on your own. Now remember, our first step is to find our u, and we have to use our ILATE, which in this case we have our algebraic before our trigonometric. So that will be our u. Now our du will be dx, our dv will be the rest of the equation, which is cosine of 2x dx, and our v will be the integral of our dv, which we will solve on the side over here. Now this will require a simple u substitution, so our u will be 2x, our du will be 2 dx, our dx will be du over 2, and our final integral will be 1/2 sine 2x. So that will be our v. Now that we have all of our variables, we can plug it into our formula. Our u is x, our v is 1/2 sine 2x, and then we are subtracting the integral of our v du, which will be 1/2 sine 2x times dx. Now with this integral, we are instructed to do another u substitution, which, let's take out our 1/2 sine 2x dx. Now let's make our u 2x, our du 2 dx, and our dx du over 2. Now we will replace our 2x with u and our dx with du over 2, which is basically the same as the constant 1/2 times du. So we could take that 1/2 outside the integrand and multiply it with the other 1/2, which gives us 1/4 times the sine of u du, which in turn gives us negative 1/4 cosine 2x. Since we plug back in our u, we will now bring our first part of the equation down and plug in what we just received. We can further simplify with this double negative to make it positive, And lastly, don't forget your plus c. Now this next problem will be a definite integral, so let's write it down. With the starting process and plugging everything in, nothing's really changed. It's still about the same way, where we use our Lie method to find u, which we will set to our logarithmic equation, and then using the rest of the equation as our dv, which is 2x plus 1 dx. Now we will differentiate the u, which we will end up getting 1 over x plus 1 dx, and then we will integrate our dv to find our v, which is a fairly simple integral, but we'll go through it anyway. The integral of 2x is 2x squared over 2, and the integral of 1 is just x, so we're left with x squared plus x as our v. We can then plug in all of our variables into our formula, and now this is where things will start to change. When we plug in our uv, we want to make sure that we evaluate it with our bounds, which is 0 to 1. And then when we do the second half, we want to also put our bounds in the integrand. So the integral from 0 to 1 of x squared plus x times 1 over x plus 1 dx. Now we'll give some attention to this first half later, but for now, let's try to integrate this second half. This is practically the same as integrating from 0 to 1 x squared plus x over x plus 1 dx. Now if you notice, in the numerator, we could just factor out an x, which will lead us with x times x plus 1 over x plus 1 dx, and it cancels out perfectly. We are then left with one of the most simplest integrals, the integral of x bounded from 0 to 1 dx, which we know will give us x squared over 2 bounded from 0 to 1, which will get us 1 half minus 0, which equals 1 half. And that is our second half. Now we can bring down our first half and subtract the second half from it. Now let's try to focus on solving this. And to solve for this, we're just going to plug in our bounds, which will get us ln 1 plus 1 times 1 plus 1. And we don't have to subtract a 0 because we know that will just leave us with this portion. So our final answer for the left side is just going to be ln 2 times 2. And you can prefer to just put it in the front if you'd like, and then minus 1 half. And that is our answer. So what can we take away from a definite integral in comparison to the indefinite integral? Just remember that with your first half, you also bound it and solve for it. And of course, alongside with our second half, we also bound it and solve for it. Now, I would like for you to solve this definite integral on your own. Now, one thing you might be confused on is, well, this is called integration by parts. Where are the parts? We only have one part. And so if you were to try to use u substitution, it would not cancel anything out and you would just be left with nothing. So it would just be inverse tangent of u, which is kind of a nothing. So in this case, we'll choose our u to be our inverse trig function, which is inverse tangent 3x, and then our du would just be the derivative of that, which if you don't know your inverse trig derivative identities, just know that inverse tangent of x is equal to 1 over x squared plus 1. So using chain rule, we know our answer is going to be 3 over 3x squared plus 1. Now our dv is going to be the rest of it, which is just simply dx. Or you could write 1 dx if that helps as well. Our v is going to be the integration of 1, which is just simply x. Now that we have all of our terms, we could simply just plug it in to our formula, which will get us the inverse of tangent 3x times x minus the integral of 3x over 3x squared plus 1. Now, if you haven't noticed, we are missing something, and that is our bounds. So let me bound our first half by 0 to 1/3, as well as our second half from 0 to 1/3. Again, I prefer solving the integral first before solving our first half, so let's do that. In this case, we can perform a u substitution, making our denominator our u. So our u will be 3x squared plus 1, which is also the same thing as 9x squared plus 1, and then our du will just be 18x, because it's just a derivative of this dx. That leaves our dx to be du over 18x, which we can plug in over here. I apologize for leaving out the dx over here. And that will leave us with the integral from 0 to 1 over 3 of 3x over u du over 18x. Now if you notice, this just makes a fraction and the x's cancel out, which is a constant, not the x, the numbers, which will simplify to 1 over 6 on the outside. Now, if you haven't noticed, my bounds are wrong because we did a u substitution, right? So we have to plug in what our previous bounds were, which is 0 to 1/3, and our u, which will give me 1 to 2. And then we are simply left with 1 over u du, which finally leaves us with 1 over 6 ln of absolute value u. And again, remember, absolute value is very important when integrating 1 over u, and then evaluated from 1 to 2. And if you're wondering why this negative sign is here, I'm sorry if that caused any confusion. I just brought it down from here, so it'd be easier to just bring down this equation right next to it. And as you can see, it's just our left-hand equation subtracting from our right-hand equation. And now we can fully evaluate these, which will just end up giving you 1/3 inverse tangent of 1 minus 1/6 times ln of absolute value 2. And that is our final answer. Now last and most definitely least is tabular method. I don't catch myself ever using this, but we were taught it, so I might as well teach it. The use case of tabular method is when your u is a high power polynomial. So for example, let's say we take the integral of x cubed cosine x dx. Well, in this case, we would choose our x cubed as our u, right? So that is considered a high power polynomial. We then set up this three-part table, which has our u as well as our dv, and then a plus and minus. Now we are going to find a derivative of this over and over and over again, and we are going to find the integral of this over and over and over again. So let's set up the plus minus. It's typically in order from plus to minus, the plus to minus, the plus to minus, but I don't have to put all of that yet. Now our u is x cubed, and our dv will be cosine x. Now we will put a negative sign and then differentiate x cubed, which is just 3x squared, and then we could just differentiate 3x squared, which is just 6x, and then we could differentiate 6x, and that's just 6. And then we can differentiate 6, which is just 0. And yeah, that's basically the end goal, is to get to 0 for your u. Now, the integral of cosine x is just sine x. The integral of sine x is negative cosine x. The integral of negative cosine x is just negative sine x. And the integral of negative sine x is just cosine x. And then don't forget your plus minus plus minus. And yeah, from here, we're just going to take the product slash multiply the first two, and then the second one. We just ignore this guy. He's gone. And then we do that here, we do that here, we do that here. And then obviously this is just 0. So that'd be 0. And then we just add up the product of every single one, which in this case, a positive times x cubed times sine of x will just lead us with x cubed sine x. Multiplying a negative times 3x squared times negative cosine x will just give us positive 3x squared cosine x. Multiplying a positive 6x and negative sine x will just give us a negative 6x sine x. And let me just bring this down here. Multiplying a negative sine, a 6, and a cosine x will just give us negative 6 cosine x. And then obviously a positive, a 0, and a nothing will give us 0, which you obviously don't have to put a plus 0. And yeah, that is basically the tabular method. Like I said, I will never use this. Even in a test, if I'm given a high power polynomial, I will never use this.